And today's topic, the topic of my presentation is block copolymer organogels, which are a new kind of materials, and it has numerous potential in applications. So let me start. So I come from this part of India, which is very near to the coast. And this is our university, and this is the building where our center is hosted. So this is the plan of my talk. So first I will introduce to the subject, main subject of today's talk. And then I will tell how the organogels can be synthesized. Then we will go to the results and discussions obtained on some kind of experiments using these organogels. And then we can see how we can take these materials forward and look for possible collaborations. So I think most of us know that what are polymers. They are nothing but they are long chains which have small repeating units, and those repeating units are called monomers. So many monomers form these polymers. So if you have only one kind of a monomer, then we call it as a homopolymer. And when you add another monomer to it, we call it as a copolymer. So, and when you have a random distribution of two kinds of monomers, A and B, then we call it as random copolymers. And if you have alternating arrangement of A and B monomers, we call them as alternating copolymers. And this block copolymers, which I will be talking about in a few minutes, they have small chains of monomers A and monomers B, which are arranged in a specific pattern. And then we also have graft copolymers. Also, when we start with polymerization, we see that there are different lengths of polymer chains we can end up, and accordingly, the molecular weight of this polymer also changes during synthesis. Also, we can control the molecular weight depending upon the polymerization technique which we choose. So, not all polymerization gives one single kind of molecular weight. So there will be always a kind of distribution in molecular weight. And because of this distribution, some kinds of properties also arise. The second topic of interest in this is gels. I hope many of us come up with gels every day, like toothpaste, hairstyling gels, the silicone hydrogel, islands, jellies, and the ultrasound conducting gels. So what are gels? Gels are nothing but they are three-dimensional cross-linked polymer network which are dispersed in a medium. So if this medium is, say, for example, water, then we get hydrogels. And here in this picture, you can see these junctions where these polymer chains link, they are called the cross-link points. If we have this medium as water, it is a hydrogel. If we have the medium as an organic liquid, sorry, there is a correction here. If it's an organic liquid, then it is called an organogel. If there is nothing, just air in the polymer, then it's called an aerogel. So aerogels are the world's lightest solids, and they are very useful in space missions as they are very good thermal insulators. So in this picture, you can see this is the world's lightest material, which is a graphite-based aerogel. It just stands in a flower. And so this is the main topic of my presentation today. It is a block copolymer, which is polystyrene block vinylpyridine. It is a diblock. That means only two monomers have been used, polystyrene and vinylpyridine. So the polymerization which has been adopted for synthesizing this diblock copolymer is reversible addition fragmentation transfer polymerization, which is in short named as the wrapped polymerization technique. So we use all these chemicals and end up with this polymerization. And then we remove this. So here, whatever you see, DD mat, it is the chain transfer agent. So first it attaches to the styrene. And then we heat it for 70 degrees in A, B, and DMF, and then vinylpyridine. And for after 24 hours, we get this block copolymer along with this chain transfer agent. And then this chain transfer agent is removed by treating it with peroxide. So this is the diblock copolymer. Now we convert this diblock copolymer into an organogel. So first time this is the first report where we found that a polymer can be converted to an organogel using cross-link. So it is dibromododecane. So you can see the two polymer chains have been linked using this dibromododecane, and heating it at DMF and 70 degree results in a gel. So the before gelation it is a liquid, and after heating it at 70 degrees it ends up as a solid. That's the gel. So here we saw that heating at 70 degrees for 4 hours resulted in a gel, whereas if we leave the solution for almost 2 weeks without any heat treatment, it can also gel the sample, but heating was found to fasten the process of gelation. After having synthesized the organogel, we did first-hand spectroscopic tools like NMR and FTIR to find whether really an organogel has been formed. And here you can see the NC bond of pyridinium ions in the polymer. So this groups have been formed in this from FTIR, and from NMR also you can see these peaks have been formed, which confirms that there is an organogel formation. And in a dilute solution of the diblock copolymer, we did some cryotem to see whether what is the shape of the micelles. They form spherical micelles, which are approximately 20 nanometer in dia. We also did small angle X-ray scattering in the physical chemistry lab at Lund. So this is the Sachs profile of a 2.8% diblock polymer. And so whatever you see at the bottom are the 0.1, 0.4 and 0.8 weight % samples without heating, but it has the crosslinker DBD in it. Whereas after heating this 0.8 weight % sample, it has developed some spectral correlations. So some kind of a structural ordering is developed. And then we fitted this Sachs profile to a polymer micellar model form factor, which is this equation. And from the spectral peak position, we found that the average interparticle spacing is about 20 nanometer. That means in the gel, the micelles are almost touching each other. We also did some light scattering measurements where you can see that in the samples which are very dilute, they just decay fast, whereas there is the correlation functions show complete arrest. So the sample is also non-flowing, so implying that it is a gel. And from light scattering, we obtained a radius of about 9 nanometers. So this, as well as the micellar size and Sachs details, confirm that the size is almost of about 20 nanometers. We also did some rheological characterization on these polymers, and you can see here that before heating, the mixture of the block copolymer and DBD, it shows viscoelastic fluid, and G prime is greater than G double prime is greater than G prime, and this implies it has viscous nature. Whereas after heating, you can see that G prime and G double prime both are independent of the frequency in which the experiment is carried out, and G prime is almost an order of magnitude greater than G double prime. This indicates that this gel, whatever we have, it has solid-like nature, and it is formed during this heating process. After that, we check the stability of these gels. So first, we can see that we use as for any applications, especially with water, we have to see how the gel responds to various pH, and you can see that we don't see much of an increase in the swelling degree of with various pH. and also in sodium chloride. So not much, maximum of 4% only we see the swelling. And at 7, we saw after forming the gel, we also did rheological measurements as a function of temperature to see whether there is any deformation happening in the gel. And we, as with temperature, we see it is still independent. Then also we did some load bearing characteristics for this gel on various weights, and up to 50 grams, we did not see any cracks or any deformation happening. And beyond 50 grams, yes, from 65 grams, we see that the gel was about to crack. So this is the SEM image, which is taken in an environment sim, the pores of the gel. And so they have very high porosity, high surface area. So the idea was like, because it has N plus group in it, whether it can adsorb dye molecules, and whether we can make reuse, in case if it does, whether we can reuse these gels and we can recover, or if there is any kind of a specificity in this gel. So first here you can see this is the dye solution. So this is the gel bit, which is about 2 weight percentage. It is being put in a methyl orange solution. Then this is Congo red, brilliant blue. Then this is bromocresol green. And this is a mixture of all these 4 dyes. And this has all these dyes along with a cationic dye, methylene blue, this solution. So, and you can see this is the result taken after 60 minutes. And here we can see that the material was able to take a very high amount of the dye within this 1 hour time. And particularly, these are all anionic dyes. So it could remove, though even say for example, a textile effluent, it has a mixture of dyes. So this, we here prove that this gel can be able to take all the anionic dyes within an hour or so. And now the specificity of the dye. So here it has anionic and cationic dyes. So when you mix all the anionic dyes, you end up this color. And now we added this methylene blue, which is blue in color. And you can see that the gel, after taking, it leaves the cationic dyes separately. So it is specific only towards anionic dyes. So, so the idea was like whether it proceeds by chemisorption or by electrostatic attraction between the reactive sites, especially the N plus groups and the ionic groups of the dye molecules. And then it is only the electrostatic attraction, because the pyridinium cation in the organogel, that is the N plus group, and the anionic sulfonate group. So all these groups have the sulfonate groups, they get binded, and that is how the dye removal is happening. We also monitored how the UV spectra evolves for the various dye molecules after contact with the after contact with the organogel. So here we see the almost negligible peaks, concentration. So most of the dyes get adsorbed. And this is for the mixture of methyl orange and methylene blue. And here we end up with only the methylene blue. And this is for malachite green and the other dyes. And here also we end up with this. So this dye, so this gel is specific to anions. And we also calculated the equilibrium adsorption capacity of the organogel. And we found using this expression where C naught is the initial concentration of the dyes, and then this is the equilibrium concentration. This is how much organogel we have taken and the volume of the dyes. And we found that we get about 600 milligrams per gram of the dyes is being absorbed. This is for methyl orange dye, then Congo red, these are for the brilliant blue, and these are for the bromocresol green dyes. We also found which is the optimized concentration of gel which we have to use for the experiments. And so this is for 0.5 weight percentage, 1 weight percentage, 2 weight percentage, and 3 weight percentage of the dye. So we don't see much of a difference between 2 and 3 weight percentage, and so we have selected 2 weight percentage of the organogel to be our optimized gel for the concentration for these experiments. And we also found what kind of adsorption isotherm it forms. So if we have a Langmuir isotherm, it follows the homogeneous surface adsorption, whereas if we have Freundlich model, it is the heterogeneous surface adsorption phenomena. And so we try to fit our the adsorption profile with these adsorption isotherms of Langmuir and Freundlich, and we found that we could get the best fit for the Freundlich isotherm. And so this adsorption process proceeds via a heterogeneous process. Then we also, for any application process, we also should know whether the material can be regenerated and reused. So here you are seeing the plot of removal efficiency and the number of cycles in which the gel has been used. So what we did was, first we put the gel in the dye solution, then after 60 minutes measure the concentration of the dyes, then put it back in an alcohol solution, get rid of the dyes, and then see that almost negligible UV spectra profile for this dye should come, and then again put back in the dye solution, and this procedure is repeated for almost 20 cycles, and we could see that it was still holding almost above 90%. And we could not see any visual deformation or swelling or cracking in the gel during these 20 cycles. So since we did not see any visual deformation, we should also see whether at the structural level any difference is happening. So what you see here is the gel, the NMR spectra of the gel before putting in for the first trial, then after 20 cycles, and also the FTR profiles of the gel before and after 20 cycles, that is the regenerated one. We don't see much of a difference, and so yes, there is no structural changes happening in the gel. So then we made a chart or table on the removal efficiency of this quaternized gel. So, and we found that it was almost beyond 90%, even after 20 cycles. So this gel material, so we can recycle it, we can regenerate it, and also reuse it, and also we can recover the dyes back. Then this is another kind of an organogel which is used, it is made of this poly N isopropyl acrylamide, which is a thermoresponsive polymer, along with 4-vinylpyridine, which is a pH sensitive polymer. So similar to the earlier polymer, so we follow this procedure and then cross-link them with a DBD, and then you can see this solution after treating it at 70 degrees for 6 hours, it gels. This material is apart from like the earlier material, we tried only dye adsorption. Here it also exhibits antibacterial activity. So we tried for Pseudomonas aureus and Organosa by zone diffusion and by the disc plating method. Here you can see that it also exhibits antibacterial activity. And another important thing is that this gel was able to remove heavy metals. So we did arsenic and chromium ions removal in sodium arsenate and potassium dichromate solutions. So, and we did ICP-OES to find how much metal ions have been reduced, and arsenic has been taken from 100 milligram per liter to about 34. So 66% of the heavy metal anion has been uptaken. And for potassium dichromate, we found the chromium ion concentration is removed to about 72%. So this is the short presentation of mine. And so both of these materials, organogels, they are one material which can be used for multiple purposes, like waste and groundwater treatment, where we can remove the dyes, especially textile effluents. Textile effluents also have heavy metals. And then water, most of the lagged water which has microbes, that can also be removed using a single material. So now let me propose to this group for our working together. So I come from India and we face a lot of these problems. So this is the textile based effluent coming up and it is just dumped into rivers. We also have the ports where most often we face this oil spills from ships. And then some states in India have very large quantity of heavy metals in groundwater. So, and people end up with a lot of diseases, death, and even in blood, breast milk, also arsenic concentrations have been reported from India. And we also have plenty of vehicle pollution coming up. So whether we can work towards this. And so I started this collaboration with Kim. So she's working with soot. So we would like to try whether these gels can trap soot. So the idea is like this. So there are a lot of reports where polyurethane foams are used because they're very light and it can float in water. And so by certain kind of functionalization, there are reports where they were able to trap oil. This is a polyurethane sponge, which is functional with graphite, which also shows oil spill recovery. So this is oil, whereas this is water. And then also polymer functionalized graphite sponges, where you can see that it almost absorbs all the oil. These are all crude oil based experiments. So we started with a similar experiment. And so this is the polyurethane sponge, which we have used, and it is functionalized with our organogel. So all the pores are coated, the linings of the pores are coated with this organogel. So this gel, which initially absorbs water, now turns hydrophobic. And this is a fully oil soaked sponge. And when we just use it, you can recover back the oil. Now we would like to try this for soot as well as for dyes. And with this, I will thank Kim for providing me this opportunity to present in this forum. And I also thank all the speakers, all the audience for listening to my talk. And I will be happy to take questions. Thank you so much.
Thank you so much, Brijitta. Very nice. I like it very much. And actually, in the network, we have more people, but this time they teaching. So many of them absent today. But I think the ideas for the collaboration, as you mentioned, is very clear. And also we open the opportunity for other people from other countries. For example, in Vietnam, the pollution is also very serious. Yes. So we hope we can have a more collaboration between Europe and Asia.
Yes.
So by that, I would like to ask if any of you have a question for Brijitta. Yeah, please, Eric.
Very interesting talk. Very interesting work, and I think this sounds like a very good material to continue to work on. Have you applied it? I mean, yeah. How far have you come? I mean, it's research, but have you taken it to some kind of product that you can use for cleaning of water, for example?
We have made a pilot plant in my university where we made a disc. So now, you know, this process is of making this polymer as such, it's little, I would not say it is cost effective. That's the reason we have now gone with the sponge, because you need to coat the sponge very less material. So we tried with a disc based of this pure polymer, which I was showing initially, and it's only a pilot plant. So we arrange technical meets with various companies, so where they come and visit this plant and then go. But so far we could not, because the main aim, we could not convince. The main thing was that it is little expensive. But so that's the reason now we are trying with the sponge. And so I think the cost can be brought down by about 1/20th of that with this. And then we would like to take it to the commercialization process.
So can I continue with one more question?
Yeah, yes.
So when it comes to soot, I mean, the soot is, I can understand that it's possible to catch soot, but how do you think one could clean and recycle this aerogel? Is that...
So pardon? It's not an aerogel. So this is an organogel. Yes. Yeah. So the idea was like, now Kim will send the samples. Then we would like to try with our material in this a sponge-based exhaust filter and see how much it has trapped. And then see, because soot as such is not ionic. So there is no kind of a bond which is going to trap it. So we would like to functionalize our gel in such a way that it will have some star block kind of material, which can, like say for example, zeolites. Zeolites can hold small molecules, which can trap them. So some kind of a star arm block copolymer, which can trap carbon-based materials. So this is not the exact organogel which we'll be trying for the soot-based material. It will have less, smaller pores, but numerous, and then it should hold about less than 10 nanometer particles. So that is the aim for soot.
I saw your paper in Langmuir, together with physical chemistry in Lund.
Yeah.
Have you had a long collaboration?
I was a postdoc in Lund with Peter Schuttenberger.
Okay.
So I came back in 2019. I was on deputation as a postdoc for 2 years.
Okay.
Then I came as a visiting researcher in 2020.
Okay.
So that collaboration was with Ulf Olsen.
Okay.
That is the reason why I know her, Perik.
Yeah. Okay.
Her daughter and my daughter in the same international school.
Okay.
Yeah, we are friends here.
Yeah.
Yeah. And yeah, thank you. Very interesting question too. Before we go with the next question from Nghi Pham, he's associate professor in Paris Saclay in France. I would like to tell you about Mika in Poland. She worked with high resolution TEM. And I think Mika also want to have a collaboration with all of us, because now I would like to have a collaboration with her to see the soot particle using high resolution TEM image. So hopefully in the future, if Brijitta or any of you want to have a collaboration with Mika, I think Mika, you want to say something?
Hello, everyone. It's true. I am working on transmission electron microscopy. So we have, in my opinion, very nice equipment in our university, and I am working with many different materials. To be honest, I start with steel, with ceramic materials, with composites, but also I am very interested in small particles. I'm not sure if my instrument will be useful for organogel and similar, yes. it will be very challenging because
Yeah.
those materials.
If it is cryo, yes, we can do a little bit.
No, no, it is not cryo. It is designed for steel, yes. So we use very high voltage. But I am open, yes, we can try.
Yeah. Yes, definitely. I will also go through your profile and then see how we can work together.
Yes.
Thank you, Nika. And more of us are physicists. Actually, I know here there is one chemist, Nghi Pham. Yeah, right. An associate professor in Paris Saclay.
Thank you. Hello, everyone. Do you listen to me?
Yeah, we can hear
Okay.
you. But it's
I'm
better if you can have a webcam and then we can see you.
I'm sorry. I'm at work and my computer at work do not have a webcam. I only have this my call. So maybe next time I will try with my laptop. Thank you very much for organization of this the kind of seminar, and thank you for the presentation. It's make me remember my work a long time ago, about 10 years ago, when I was a postdoc, because nowadays I'm working on ceramic material for application in thermic and electric measurement. However, when I work on postdoc, I was working also on organogen and aerogen both, and that's why I see several interesting points here. However, my first question is, when you use your gen for absorption experiment, is organogen or aerogen? It means dry one or wet one?
No, it still has BMF in it, so it is an organogel.
Okay, so it means that when you need to do several circle to study, I wonder how could you manipulate your gen so you can put in the solution, remove and maybe release the molecule,
The dyes.
the dye. How could it work?
So you put them back in alcohol.
When you put
so
in,
the dyes.
When you put back in alcohol, the gen is still gen, or
Yeah, it is still
it
a
become
gel.
liquid. Okay.
No, it will not become liquid.
Yes.
It is still a gel.
Yes. One moment you show the absorption capacity when you absorb up to 100 or a few hundred ppm of the dye. I'm wondering, it means that the organogen should be how to say, because you could insert several quantity of the molecular dye molecule. So it means that the organogen should not be such compact.
No, it doesn't take water. It just takes the dye molecules. So the sulfonate groups
but
in
the
the dye
dye
just
molecule
get
are big enough. It's not the iron. It's organic molecule.
Yeah. So, but it has also pores in it, right? So they get trapped in.
Okay. Okay, for the organogen, do you try to measure the temperature of the transition between gen and liquid phase? Do you understand me?
Can you
Yes,
ask the question again?
gen, it means that you should they should exceed a temperature at which the solution containing of the molecule become gen.
Yes,
and
that happens at.
Yes.
It happens at 70 degree.
Okay, 70 degree is not the temperature where you use to dissolve, but to obtain gen. Okay, 70 degree Celsius. And this temperature, do you try to study if this temperature depend on the concentration of the gen or not?
No, I couldn't understand the question.
Okay, when you try to measure the temperature of the for each organogen, it should exceed a temperature at which above this temperature you have gel, lower than this temperature you
No.
should no.
So we made the gel at 70 degrees, and once you cool it back, it is always a gel at all temperatures. So
Okay, so it's irreversible process.
yes, it's an
Okay.
irreversible gel.
Okay. So from this gel, my last question, if I still have time, I'm sorry.
Yeah.
Do you try to dry the gel or not to obtain aerogen, which he proposed at the end of your presentation when you talk about the material? I suppose that is a aerogen.
You mean the ionogel?
Yes. At the end, when
Yeah.
you when you propose the application for oils, absorption and else, I suppose that it should not be organogen, but is aerogen.
Maybe I have to go through it to verify your claim, but I will go through it.
Yes.
Yeah. Thank you.
Okay. Thank you.
Thank you, Nghi. The question from chemist is different from physicists. Yeah, very difficult question.
Hi, Brijitta. I
Yeah,
have one question concerning the molecular structure that you have, because the copolymer have very complicated structure. When you measure the NMR and FTIR, it only give you the bond, like identifying what kind of bond structure, but you cannot see the whole chain structure.
Yes.
If the sex, what are the resolution of the sexes give you? Can it?
Hello?
Does it give you also like the molecular structure of this copolymer?
Sacs, you mean?
Yeah, the sex that you measured in Lund.
Yeah, so in sacs, the problem was like, though we could fit with a polymer micelle model, we could not fit for the structural peak with the existing models.
Okay, so you only get the the shape of the micelle from the polymer.
So only from the Q position we found that approximately the two micelles will be touching, and that is what we found from the structural peak. But we tried various RMSA models and to fit into this structural peak, but none of the models, it was always giving an overestimation of the values.
If you have like higher energy in sex measurement, that means you may have a better spatial resolution. Do you think it's possible that you can resolve the molecular structure of polymer?
So actually this sacs measurement was done using the Ganesha instrument in physical chemistry, but I think if we go to synchrotron based measurements, then we may get good resolutions.
Okay, thanks.
Thank you, Thái, for your question. And the next question from Wang. Yeah, you can go ahead, Wang.
Okay.
Yeah.
Okay. So may I have a question? When you measure with the removal efficiency, so did you use it with a contact angle measurement? Is that correct?
Pardon?
When you measure with the removal efficiency, so
yes.
Did you measure with a contact angle measurement? Is that correct?
Yeah, so we put the gel in contact, and while measuring we remove the gel.
Okay. So because I'm working with your hexagon boron nitride, so then we also would like in the future we would like to measure, for example, like drop some oil or dye on the top of my sample with the surfaces and measurement with contact angle measurement, something like that. So maybe in the future I will contact with you. So we will do something with together.
Definitely.
Thank you so much. Yeah. Thank you.
Yeah, hopefully we will have a more collaboration between us.
Yes.
Yeah, the next question from Hun. Hun is he working in UK now. Yeah, Hun, you can go with your question, please.
Thank you, Go, for the introduction, and thank you, Britta. Hopefully, I pronounce your name correctly. For your very interesting talk. I think between you and me have a lot of mutual interest, because I'm working on molecular response. All type materials have a molecular response, including metal frameworks, zeolite, and aerogel as well. So related to the aerogel, the question about how to convert the gel to aerogels, I have a equipment using supercritical fluid to remove the solvents from gel to turn into aerogel. Yeah, relate to your talk, I'm really interested in how you investigate the mechanism of the reactions. So do your gel materials have a photo and it has any photo redox activity associated with this type of materials?
So actually we are also working with the Indian Space Program. So they have been looking for thermal insulators. So it was them who proposed that whether we can work with an aerogel, but we don't have any supercritical fluid extraction facility in my lab or in nearby IITs. So though we have the silica-based gel, it is just lying there with the solvent in it. So maybe then I can write to you that whether we can associate.
Yeah, of course, yeah. That is about collaboration. Relate to your talk about using gels in remove the dyes. I'm really interested in how you investigate the mechanisms. And my specific question is, do the gels materials have photoactivities?
So as what we have done is only we have been following only the adsorption isotherm models, and no kinetic monitoring has been done.
Right. So from that point, now I wonder how do you distinguish the chemical absorption and the electrostatistics in your materials in the
no, so we because we've been working on different kinds of gels, and we found that only this pyridinium group, if there it is there, so N plus and SO3 minus. So we did some of the pure the dye adsorbed gel, and also found that there is a linkage happening. And then if you put it in a strong sulfate, more affinity, then it was absorbing not the sulfate group, the other groups.
Okay. Yeah. So you suppose that they have already like physics options, right?
Yeah. But if you have facility which can tell that yes, this is how it proceeds, then we can work together.
Okay. Yeah. Thank you very much.
Thank you, Wong, for your. You get a cold, maybe?
Yeah.
The same to me.
Yeah.
Nghĩ, you have another question?
I think it's okay. Thank you.
Okay, yeah. I would like to take the chance to introduce another people in the network. So we know each other better. Yeah, because the purpose is to build up the collaboration. We have a Sandra Torok. She is also from the Sud group in Lund. She have just a defense, very successful her defense recently. Sandra, yeah, she's smiling. Then we have another network member, Yui. Yui working on combustion community in France, and but not in the food community, but in combustion. Yui, can you show up and say hello to other people? We cannot hear you. Yeah.
I can take the chance to just say hi. Yeah, I didn't know if I should say something, but it's, thank you for today. Bye.
Maybe, thank you, Sandra. Maybe you have some problem with his computer. And we have two other people, Vũ Ngọc Hải and Phúc Phạm. You are new, so I don't know you. If you want to take a chance to introduce about yourself, you're really welcome. Yeah, maybe they are a little bit shy.
Yeah. Hi, is my colleagues, and then he worked together with me, and then maybe he have a phone or something, moving back and forth somewhere. Yeah.
Yeah, you said in the chat that maybe he have some problem. Yeah, microphone doesn't work, he's told me. Yeah, so thank you very much everyone for today, especially the speaker today, Brijitta, for your very interesting talk. And we will actually now in Lund, I and Soga is sampling the sample, and Soga helped me to measure some measurement before sending the sample to you. So hopefully we will finish soon and send it to you.
Yes.
So I will let you know later. So this week I take off 1 week for sick leave and take care of my children before they are sick too. Next, at the end of this month, 27 October, we have a very interesting talk. This is inspirational seminar from a professor, Ngô Hà Dương, in Berlin, Germany. He will talk about macro sensor and also how to success with application. So I think it's very useful for all of us, especially the young people, to know how to write a proposal. So welcome all of you in the next event, and thank you very much.
Yes.
Yeah.
Thank you, Kim.
Okay.
Thank you.
Thank
all of
you. Bye bye. Yeah. Bye bye.
Thanks,
Yeah.
Phương.
Thank you so much. Yeah.
Thanks,
Bye bye.
everyone.
Yeah. Yeah. Bye bye. Yeah.
Right.